Hello juniors, today we're going to continue with the chapter about rational functions, and we're going to get into electronic assignment 31, which is called rational functions. And you'll see the slight difference that there is between what we know as a reciprocal function and what we're now going to study as a rational function. They are slightly different things, but the function itself is still the same. We're always talking about hyperbolas when we talk about either reciprocal or rational functions, okay? So rational functions, the objectives for the class: number one, determine vertical and horizontal asymptotes, and number two, identify rational function and its graph. Okay, so let's start by analyzing a real-life application of this about rational functions. And it says, have you noticed the way the sound of a siren changes as a fire engine or police car passes you? This normally occurs when we are in traffic, right? Whenever there's an ambulance approaching us from behind, we tend to hear the siren both faster and louder, right? And when the ambulance passes by, then we start hearing the siren a little bit slower and also more quietly, right? It says the observed frequency is higher than the emitted frequency during the approach. It is identical at the instant of passing by, and it is lower during the time it moves away. This is called the Doppler effect. Okay, this is something that maybe you have seen or you will see in physics later on. So the equation for the observed frequency of sound when the source is traveling towards you is given by this expression. So this is the frequency or the new frequency, and this is how we calculate that frequency, right? And you see that this is a reciprocal or rational function because we're changing the value of v, which is the velocity of the source, right? Okay. So it says sound frequency is measured in hertz, the number of waves per second. Okay, here it explains 330 is the speed of the sound, f1 is the observed frequency in hertz, f is the emitted frequency, v is the velocity of the source toward you, and f1 is a rational function, okay? So that's just an example, just to introduce what a rational function is. And here we have the definition. It says a rational function is a function in the form f of x equals gx over hx. That is, we have a function divided by another function, right? That's a rational function, where g and h are polynomials. So here it says h of x cannot be 0 since a value divided by 0 is undefined. So here you can notice a difference between what we called reciprocal. If you remember, reciprocal functions were like this: f of x equals k over x, right? Where k is a constant number only, right? So that's the main difference with a rational function. You see that in a rational function we're having a function as the numerator, while in a reciprocal function we're having a number or a constant as the numerator, right? So that's the difference between both. Let me write that down here for you to remember. So this is reciprocal function. I'm going to organize this better. K over x, while a rational function would be f of x equals gx over hx. Over h of x. Okay, so it says in this course g of x and h of x will be restricted to linear functions of the form px plus q, so we can investigate rational functions f of x in this form: g of x over f of x, where g of x and h of x are both linear functions. Later on in university, if you study career related to numbers and functions and function analysis and calculus and so on, you will see that there are different types of rational functions, and this function over here and this function over here do not necessarily need to be linear functions. They might be quadratic functions or cubic functions or whatever, right? But for the IB program, we're focusing on linear functions. Okay, so let's do this investigation just to see what rational functions is about. So it says use your GDC to show sketches of. So we're going to sketch this function, this function, this function, and this function, just like we did in the previous electronic assignment. Okay, so I'm going to graph those functions. The first one, x over x plus 3. I'm going to do that in Desmos. X over x plus 3. That's the first one. Then we have x plus 1 over x plus 3. So x plus 1 over x plus 3. Then we have 2x over x plus 3. 2x over x plus 3. And finally 2x minus 1 over x plus 3. So 2x minus 1 over x plus 3. Okay, so I assume that you can already notice something, right? First of all, I'm going to erase all of the functions except one. You see that the shape is still remaining as a parabola, right? As a hyperbola, sorry. It's still a hyperbola, and as you can see, we have both vertical and horizontal asymptotes. If we analyze this, where do you think that the vertical asymptote should be at? If we set the denominator to 0, we would see that the vertical asymptote is at x equals -3. If I draw x equals -3, you're going to see the vertical asymptote right there, okay? And what about the horizontal asymptote? Where is the horizontal asymptote? It seems to be at y equals 1, right? If we look at the graph. And if we sketch this, y equals 1, you will see that that is the horizontal asymptote, right? I'm going to change the color. There. Maybe this one also can. There you go. So we can see that the horizontal asymptote is actually y equals 1. But how do we find that exact value? Okay, so let's analyze this in the table. So for the first function, x over x plus 3, we know that the vertical asymptote is x equals -3. You already know how to calculate that. And the horizontal asymptote is calculated this way. Pay attention. Whenever we have a function divided by another function, which is the case of a rational function, the horizontal asymptote is always found by dividing the coefficients in front of the x's. Okay, so we need to look at the coefficients in front of the x's. In this case, we have a 1 here and a 1 also here. So the horizontal asymptote is directly 1 divided by 1. We divide both coefficients and we get y equals 1, which is exactly the horizontal asymptote we got in this example, right? So that's how we find horizontal asymptotes in this particular case. When we talked about reciprocal functions, we just saw if there was a vertical translation, and if there was no vertical translation, then the horizontal asymptote was directly y equals 0, right? Okay, so the domain is x different from -3, and the range would be y different from 1, okay? Now let's see a second example. I'm going to draw that function here. And what do you notice? You see that we have the same asymptotes. The vertical asymptote is still -3, x equals -3, and the horizontal asymptote is still y equals 1. So let me go back. The +1 that we have here, which makes it different from the first function, is actually not affecting the position of the function. It is just changing its shape. If we compare both shapes, let me plug in the function. You see that there's a slight difference in shape between the both, but the position is exactly the same. Okay, so vertical asymptote, once again, we set the denominator to 0 and we get x equals -3. The vertical asymptote follows the same rule. Coefficient in front divided by coefficient in front of the x in the denominator. So this is again y equals 1 divided by 1, which is 1. So the domain would be x different from -3, and the range is y different from 1. Then the next case. What do you think the horizontal asymptote should be for this particular case? If you understood the rule, you would notice that the horizontal asymptote in this case should be y equals 2, right? Because it's 2 divided by 1, which is 2. So let's see if we can appreciate that in the graph. I'm going to graph this function over here. And you see that the vertical asymptote is still the same, but the horizontal asymptote is now different, right? It's not y equals 1 anymore. If we do y equals 2, we're going to see that that is our new horizontal asymptote, right? So that's the new horizontal asymptote, y equals 2. So let's go back. The vertical asymptote is still x equals -3. The horizontal asymptote, using the same rule, coefficient in front of the x in the numerator divided by coefficient in front of the x in the denominator, and we get the value or the expression for the horizontal asymptote, 2 divided by 1, 2 divided by 1, which is y equals 2. So domain x different from -3, and range is y different from 2. Finally, in the last case, if we plot this function, we're going to see that it should be almost the same as the green one. Yes, but the shape changes a little bit, just like the first and the second functions when we drew them. Okay, so you see that in this case, vertical and horizontal asymptotes are exactly the same. So if we go back, we're going to say that the vertical asymptote in this case is still x equals -3. And you see that if we follow the rule, remember it's the coefficient in front of the x, the one that we divide, not this one, not this one, right? So the coefficient in front of the x is 2 in the numerator, and the coefficient in front of the x is 1 in the denominator. So once again, the horizontal asymptote will be y equals 2 over 1, 2 over 1, which is 2. So the domain is x different from -3 and y different from 2. Okay, so it says, what do you notice about the horizontal asymptotes? What we notice is that if the function is a rational function, that is f of x equals ax plus b divided by cx plus d, if we write this in letters, then the horizontal asymptote will always be equal to the coefficient in front of the numerator of the x in the numerator divided by the coefficient in front of the x in the denominator, which is in this case y equals a divided by c, right? That will be always the horizontal asymptote. Okay, so this is kind of a formula that you can remember in order to find horizontal asymptote. This formula is not in the formula booklet, by the way, so this is something that you need to know. Okay, and then part D says, what do you notice about the domain and the value of the vertical asymptote? The domain and the value of the vertical asymptote. Okay, so that's something we already know, right? The domain and the vertical asymptote are always referring to the same value, right? Which is, if the domain is x different from -3, that means that the vertical asymptote is x equal to -3. So we are always referring to the same value, right? So we can say that they correspond, or they refer to the same value of x. That is always the case in these types of functions. Okay, so What we just did in the investigation is what we know as rational functions. So rational functions in the form y equals ax plus b divided by cx plus d. And it says every rational function of the form y equals ax plus b and divided by cx plus d has a graph called a hyperbola, as we have seen already. The graph of any rational function y equals ax plus b divided by cx plus d has a vertical and a horizontal asymptote. The vertical asymptote occurs at the x value that makes the denominator 0. You already know that rule. And the horizontal asymptote is always the line y equals a divided by c, which is this number divided by this number. So basically we don't care about b and d when we look for the horizontal asymptote, okay? So here we have the graph, and you would see that the horizontal asymptote is always a divided by c, y equals a divided by c, and the vertical asymptote is always x equals negative d over c, which is found by setting the denominator to 0, right? If we set this denominator to 0, we're going to have, let me do that here, cx plus d equals 0. So if we solve for x, we're going to get x equals negative d over c, which is exactly this value over here. Okay, that's why the horizontal asymptote, sorry, the vertical asymptote is always equal to negative d over c. So it says to find the horizontal asymptote, rearrange the equation to make x the subject of here. Okay, here's a small demonstration of why the horizontal asymptote is always a divided by c. Basically what we do is kind of an inverse here. We try to solve for x, and when solving for x we see that we get this in the denominator, and by following the same rule of setting the denominator to 0, we're gonna get that y is equal to a over c, which is the expression for the horizontal asymptote. Okay, so that's just for your information. So it says the horizontal asymptote occurs when the denominator is 0, that is when y equals a divided by c. Okay, we are left with 2 examples, but I want to let me show you this quickly. We still have quite a few time. So it says sketching rational functions from the equation without using technology. So how do we sketch rational functions without using technology? It's actually pretty easy, and this is something that we have done already with the previous electronic assignments. It says the general equation of a rational function is y equals ax plus b divided by cx plus d. To sketch this function without the use of a GDC, you should, and these are the 6 steps that you need to remember, but you'll see that they are basic things, not very complicated to do. First step, find the vertical asymptote, which is found like this, setting the denominator to 0. Then step number 2, find the horizontal asymptote, which is found this way, as we just saw in the investigation. Number 3 says find the y-intercept by letting x equal 0 and solving for y. So basically find y-intercept. Fourth step, find the x-intercept by letting y equal 0 and solving for x. And then 5 says test values on either side of the vertical asymptote to determine whether the curve tends towards positive or negative infinity on that side. Okay, this is what we're going to see in the example. And finally, draw the axis and asymptotes, then sketch the curve. Okay, so let's see how these steps apply to this particular example. It says A. Find the equations of the horizontal and vertical asymptotes of this expression. Y equals 4x plus 1 divided by 2x minus 6. Okay, so let's start with that, part A. If we want to find the equations of the horizontal and vertical asymptotes, remember the rule. To find the vertical asymptote, we're going to start with the vertical asymptote. Vertical asymptote says that we need to set the denominator to 0. So we're going to write 2x minus 6 equals 0. So the value of x here would be 6 divided by 2, which is 3. So we already have the equation for the vertical asymptote. Then, if we want to find the horizontal asymptote, Remember the rule. When we have a rational function, it's the coefficient in front of the x in the numerator divided by the coefficient in front of the x in the denominator. So this would be y equals 4 divided by 2, right? Which is equal to 2. So y equals 2 is the horizontal asymptote in this case. So we already have vertical and horizontal asymptote. Try to always associate this with y equals ax plus b divided by cx plus d. If you remember that, then you won't have much trouble. Okay, so we already found the equations for horizontal and vertical asymptotes. Then we're going to go to part B, which says sketch the function, show any asymptotes not on the axis as dotted lines. Okay, so now we're able to do the sketch. We're going to do this sketch right here. Okay, we're going to do a sketch here. Sketch here. So this is x and this is y. We already know the asymptotes. We know that the vertical asymptote is at x equals 3, so I'm going to write x equals 3 here. And the horizontal asymptote is y equals 2, that's around here. So with dotted lines, I'm going to do with green. I'm going to mark the vertical asymptote. And in y equals 2, we're going to mark the horizontal asymptote. Once we have sketched the asymptotes, we still need to verify if this parabola would be in first and third quadrant, or if it is in second and fourth quadrant. In order to verify that, we need to find the x and y intercepts, right? So first of all, I'm gonna find the y-intercept, okay? To find the y-intercept, remember the rule is we need to set x equal to 0, right? So if I find y when x equals 0, we're gonna have 4 times 0 plus 1 divided by 2 times 0 minus 6. Remember, we're always doing this without calculator. So this gives us negative 1 over 6, okay, which is 0.1333 or something like that, but it's 0 point something, right? Negative 0 point something. That means that our y-intercept would be somewhere around here, maybe, kind of like here, right? And now the x-intercept, which is found by setting y to 0. So 0 equals 4x plus 1 divided by 2x minus 6. If we solve for x, if we take all of the denominator on top here, we're going to multiply it by 0, so that will still be 0. So this would be 0 equals 4x plus 1. And if we solve for x, we'll have negative 1 divided by 4. And this is the value of x. Negative 1 over 4, negative 1 over 4 is negative 0.25. So the x-intercept is negative 0.25, comma 0. Okay, and the y-intercept, I forgot to write here, it's 0, comma negative 1 over 6. Okay, so if we plot the x-intercept, negative 0.25 and 0, that'll be somewhere around here. Sorry, I just noticed a mistake here. So somewhere around here is the x-intercept, and the y-intercept actually, I plotted it wrong because it's negative 1 over 6, so it should be somewhere around here. Okay, so now that we have 2 points of the graph, we can already know that this graph is actually in the third and first quadrants, right? Because we have 2 points in the third quadrant according to our asymptotes. So we can already do a sketch here. Remember to respect the the asymptotes, and we'll get something. Oh, this would be something like this. Then it goes down until the asymptote, and here we'll have something similar, right? Comes from the infinity and then goes. Okay, so this would be a quick sketch of this function. Finally, for part C, we want to state the domain and range. The domain, if we already know the vertical asymptote, the domain would be x belongs to all real numbers except 3, right? X is different from 3. And the range would be y belongs to all real numbers and y is different from 2 in this case. So there we have the values of the domain and the range. Okay, finally, we're going to do this example quickly. Now that we know the steps in order to sketch a rational function, we're going to do this as a review of what we just studied. So it is for the function y equals x plus 1 over 2x minus 4. A, sketch the graph. Before sketching the graph, actually it's better to find the vertical and horizontal asymptotes. So we're going to start with part B. We're going to say that, let me copy this not to avoid wasting time. So we're going to say that the vertical asymptote in this case is, we need to set the denominator to 0, 2x minus 4 equals 0. So x equals 4 divided by 2, that's 2. This is the vertical asymptote. And the horizontal asymptote would be coefficient in numerator divided by coefficient in denominator. So this would be y equals 1/2. Which is the same as saying y equals 0.5. So this would be the horizontal asymptote. Okay, now we can plot this graph, and okay, before plotting, actually we need to find x and y intercepts. So I'm gonna copy this to find x and y intercepts. There. So I need to change this, and I need to change this. Okay, so y would be equal to, when we find y-intercept, we set x to 0, so this would be equal to 0 plus 1 divided by 2 times 0 plus 4, and this is equal to 1/4. So 1 point is 0, 0.25, which is 1/4. Right? And sorry, this is minus 1 actually. This is minus 1. So it's negative 1/4. So this is negative 0.25. There you go. And the x-intercept, we set y to 0. So this is 0 equals x plus 1 divided by 2 times 0 minus 4. If we solve this, sorry, not 2 times 0, 2 times x. 2x minus 4. So if we solve this, we're going to take all of this term multiplying here by 0, so that term gets eliminated. So 0 equals x plus 1. So the value of x is x equals negative 1. So the x-intercept has coordinates negative 1, 0. Okay, once we have all of that information, then we can do our sketch. I'm going to do a sketch right here. Y-axis, x-axis, x, y. So let me plot the asymptotes first. X equals 2 is right here, and y equals 0.5, that's right here, 0.5. So asymptotes, vertical asymptote right here, and horizontal asymptote right here. Once we've sketched both asymptotes, I'm going to mark the y-intercept and the x-intercept. So the y-intercept is at 0, negative 0.25. That's somewhere around here. And the x-intercept is at -1, 0. -1, 0, that's right here. So we already know where this hyperbola should be, right? It should be in the third and first quadrant once again. So if we sketch this by hand, obviously, we're gonna have the shape of the hyperbola right here and the shape of the hyperbola right here. Okay, so that is the sketch. Finally, for part C, we want to find domain and range once again. So domain is x belongs to all real numbers except 2, x different from 2. And the range is y belongs to all real numbers except y 0.5. Okay, so that's it, juniors, for this class. I hope this was clear. We're almost finishing this chapter about rational functions. It's a very easy chapter and short. So be prepared to work with some exercises about this. And as always, if you have any doubts, please let me know. See you.